Section 4.5, L'Hopital's Rule. From the beginning of calculus, we have encountered various limits, such as the limit as x approaches 2 of x squared minus 4 over x plus 2, or the limit as x approaches 2 of x squared minus 4 over x minus 2, or even the limit as x approaches infinity of e to the x over x. Sometimes we've resolved these limits using continuity, such as in the first example. Since this is a continuous function at 2, we can obtain the limit value by simply plugging in x equals 2 wherever we see an x, and we ultimately get a 0 over 4, so the limit value is 0. We could only get away with this because the original function was continuous at the x value at which we were taking the limit. But we don't always have this luxury. So in the second example, if we take the limit as x approaches 2 of x squared minus 4 over x minus 2, notice if we plug in a 2 everywhere we see an x, we get a 0 in the numerator, we get a 0 in the denominator, and this 0 over 0 form is called an indeterminate form because the final answer to a limit with this form could be anything. So remember, division by 0 is not defined. We can't just simply cancel the zeros and get a 1. That's not algebraically correct. And so we have to look for some alternate strategy on how to resolve this limit. Well, you may remember from Calculus 1 that we factor the numerator. When we factor the numerator and then cancel this common factor, we get the limit as x approaches 2 of x plus 2. But now this function is continuous at x equals 2, so we can get the limit of this function by simply substituting in the 2 to get an ultimate limit of 4. So notice in the previous example, we had a 0. In this example, we have a 0 over 0 form, and we got an answer of 4. The last example was not an indeterminate form. We just got a 0 over form. So the idea is when you have a 0 over 0 form, you need to make some kind of algebraic move or geometry move or something, at least that's what we did in the past, in order to resolve this indeterminate form. If we take a look at a different example, if we take the limit as x approaches 0 of sine x over x, as x goes to 0, sine x goes to 0, and x goes to 0, so the numerator goes to 0, the denominator goes to 0. This is not a continuous function at 0. And so notice off to the side, I write in this notation off to the side in parentheses, I write 0 over 0. I don't write equals 0 over 0. Mainly this is a notation to indicate that the limit we're dealing with is of a particular form. And as the lecture goes on, you'll see that when we encounter an indeterminate form, a very important part of the process is to know what type of indeterminate form we have, because that's going to lead us to how we resolve the indeterminate form. Now you may remember from Calculus 1 that when you have this limit, you could use a table method or a graphical method or even the squeeze theorem to resolve this, and it turns out that this limit is 1. It's not 1 because the zeros canceled and you got a 1. It's just 1 because if you use the table method or the graphical method or the squeeze theorem, then this is what the limit comes out to be. So notice in our last example, the 0 over 0 form ultimately ended with a 4, but this different example, the 0 over 0 form ultimately ends in a 1. This is why they're called indeterminate forms, because when you encounter this form, the answer could end up being anything. Yet another example is if we look at the limit as x approaches 0 from the right of sine x over x squared. This is a 0 over 0 form because the numerator is going to 0. The denominator is going to 0. But if you were to apply the table method or the graphical method, and you should check this for yourself, that this limit turns out to be a plus infinity. So we saw 3 different 0 over 0 forms, and their ultimate answers ended up being 3 completely different things. So this is why we call this an indeterminate form, because the limit can resolve to different values for different examples. In fact, there are other indeterminate forms. If you were to take a look at the limit as x approaches infinity of 2x over 3x minus 1, notice as x goes to infinity, 2x is going to infinity, and 3x minus 1 is also going to infinity. So this is another category of indeterminate forms. We call this an infinity over infinity indeterminate form. And it turns out that the answer to different infinity over infinity form examples can be different things. In this particular example, if we were to divide through by an x in all 3 terms, and then we were to simplify, here we get a 2, here we get a 3, here we get a 1 over x, and then we were to take the limit as x goes to infinity, this is just a 2, this is just a 3, and as x goes to infinity, 1 over x goes to 0, so this just becomes a 2/3. So this example comes out to be 2/3. But if we were to change this example just a little bit and take a look at the limit as x goes to infinity of x squared over x plus 1, this is another infinity over infinity indeterminate form. The numerator is going to infinity, the denominator is going to infinity. If we were to divide everything by x, here we would have an x squared over x, an x over x, and a 1 over x. When the algebraic dust settles here, we would have an x in the numerator, we would have a 1 here, and we'd have a 1 over x here. If we let x go to infinity, we can see that the 1 is just 1, the 1 over x is going to 0, the numerator is going to infinity, so the ultimate value of the limit is infinity. So once again, we're seeing that we had two different examples that take this infinity over infinity form, and they resolve to two completely different answers. This is what makes the 0 over 0 type limits be indeterminate forms, is different examples can come out to have different answers. Okay, so the questions are, what forms are actually indeterminate? We need a list of those indeterminate forms. And then secondly, how do we resolve indeterminate forms in general? What's our plan of attack? So let's begin with a starting list of indeterminate forms. We've definitely seen that 0 over 0 and infinity over infinity are two prototypical indeterminate forms. And actually, when we say an infinity over infinity form, it might be that this is a plus infinity and this is a plus infinity, or it could be a plus infinity over a minus infinity, or a minus infinity over a plus infinity, or a minus infinity over a minus infinity. We don't sweat the details on the plus or minus. It turns out that they're all indeterminate forms. So even though we casually say infinity over infinity indeterminate forms, we really mean plus or minus infinity over some plus or minus infinity, any of those combinations. So secondly, how do we handle indeterminate forms? And the answer is something called L'Hopital's rule. So it's pronounced L'Hopital's, it's not L'Hospital or anything like that. It's L'Hopital's rule, and it's written in different ways. Sometimes it's written like this, sometimes it's written with an S, but it's a French mathematician named L'Hopital. And I'll point you to the text for a formal statement, but as a short abbreviated version here, it just goes like this. If you have a limit as x approaches a of an f of x over a g of x, if that limit is a 0 over 0 or some type of plus or minus infinity over plus or minus infinity indeterminate form, then the value of the given limit is the same as taking the limit as x approaches a of the derivative of f over the derivative of g. Notice this is not a quotient rule. It's just the limit as x approaches a of f of x over g of x is the limit as x approaches a of f prime of x over g prime of x, assuming that you have an indeterminate form of 0 over 0 or infinity over infinity type. It doesn't apply always, it's only when you have those particular types of indeterminate forms. Now, equipped with L'Hopital's rule, let's revisit those same examples above. So I'll leave L'Hopital's rule on the screen so that we can see it. But example 1, this is taking the same functions from above. If we had the limit as x approaches 2 of x squared minus 4 over x minus 2, that's a 0 over 0 form as we discussed above. So now if we apply L'Hopital's rule, and I'll signify this like this so that you know what justifies moving from this step to this step. It wasn't any kind of algebra, it was L'Hopital's rule. So L'Hopital's rule says we can take the limit as x approaches 2 of the derivative of the top here is 2x, the derivative of the bottom is just 1. And now the idea is hopefully this limit is resolvable. Maybe this will be a determinate form. And it is. We can see that this is a determinate form. This is a continuous function at 2. We can just plug the 2 in and we get an answer of 4. And this is exactly the same answer we got above by algebra, but this time we use L'Hopital's rule. Okay? So now for a second example, we'll again recycle the example from above. If we had the limit as x approaches 0 from the right of sine x over x squared, we have this is a 0 over 0 form. By L'Hopital's rule, we take the limit as x approaches 0 of the derivative of the top. The derivative of sine x is cosine x. The derivative of x squared is 2x. And now we're just going to check and see if this is a determinate form or an indeterminate form. As x goes to 0, cosine x goes to 1. And 2x goes to 0. So the numerator is going to 1, the denominator is going to 0, and so that means since x is going to 0 from the right, we don't want to write equals 1 over 0, but we think of this as 1 over something that's getting closer and closer to 0 from the right. So we think of 1 over 0.1, 1 over 0.01, 1 over 0.001, 1 over 0.00001. That's getting very, very large and positive. So the limit is going to infinity. Notice here we didn't need a table method or a graphical method. We just used L'Hopital's rule to resolve the limit of this 0 over 0 indeterminate form. Marching on with our third example, if we take the limit as x goes to infinity of 2x over 3x minus 1, this is an infinity over infinity indeterminate form that we discussed before. We can apply L'Hopital's rule. The derivative of the top is 2. The derivative of the bottom is 3. This limit is very straightforward now. The limit is just 2/3. So notice L'Hopital's rule is a very efficient tool for, in many situations for resolving these 0 over 0 or infinity over infinity indeterminate forms. Once more, if we take the limit as x approaches infinity of x squared over x plus 1, the numerator is going to infinity, the denominator is going to infinity, so L'Hopital's rule is applicable. Take the derivative of the top, we get a 2x. Take the derivative of the bottom, we get a 1. As x goes to infinity, 2x is going to infinity, so the answer to this limit is infinity. Okay, so notice again, two different indeterminate forms had two different ultimate answers. That's what makes them indeterminate forms. I happen to just use examples here that they were all infinity over infinity, but it could have easily been an infinity over a minus infinity or a minus infinity over a minus infinity. You'll see those kinds of things in the homework. So some other indeterminate forms that we need to be aware of are 0 times infinity is an indeterminate form. Infinity minus infinity is an indeterminate form. And then we have the indeterminate powers, 0 to the 0 and 1 to the infinity. You need to be aware that these are indeterminate forms, but they're not directly, L'Hopital's rule is not directly applicable to these because L'Hopital's rule doesn't just require the function or the limit to be an indeterminate form, it requires it to be an indeterminate form of 0 over 0 or infinity over infinity type. So we'll see in just a minute, when you encounter one of these other indeterminate forms, we may need to do some algebraic manipulation to rearrange the given problem so that it is a 0 over 0 form or an infinity over infinity form, and then we can apply L'Hopital's rule. It's also very important to realize common things that you may run into that are not indeterminate forms. So for example, infinity plus infinity is not an indeterminate form. 1 over something that's going to infinity is not an indeterminate form. Infinity over 1 is not an indeterminate form. Another example would be something like 1 over 0 is not an indeterminate form. So you need to be very aware of what type of forms are indeterminate and that you need to work towards a L'Hopital's rule resolution and what types of indeterminate forms, what types of forms are not indeterminate. And you realize that I know how to do these without using L'Hopital's rule. Let's take a look at one of these other types of indeterminate forms. So for example 5, if we take the limit as x approaches 0 from the right of x ln of x, notice as x goes to 0 from the right, x is going to 0, so this term is going to 0. ln of x is going to, if you look at the graph of the natural log function, as x gets closer and closer to 0 from the right, ln of x is getting closer and closer to minus infinity. So this is a 0 times a minus infinity. We just casually call this a 0 times infinity, but when I do this, I try to speak with as much precision as I can, and I'll write this as 0 times minus infinity. But whenever we deal with one of these infinities in these forms, here, this can be a plus infinity or a minus infinity. It doesn't matter. So we need to rearrange. We can always rearrange a 0 times infinity indeterminate form to turn it into either a 0 over 0 form or an infinity over infinity form. Like for example here, this isn't even a quotient, so we know we can't use L'Hopital's rule. But if I algebraically rewrite this as an ln of x over x to the minus 1 power, notice I just export this to the denominator. These are algebraically equivalent. And I've accomplished two things here. This is looking more and more like a L'Hopital's rule applicable problem because it's a quotient. But also, if you stare at this now, the numerator as x goes to 0 from the right, the numerator is going to minus infinity. The denominator is also going to minus infinity. I'll fix that. is going to minus infinity. And so this is a infinity over infinity indeterminate form. And so we can use L'Hopital's rule here. By L'Hopital's rule, we take the derivative of the top, we get a 1 over x. We take the derivative of the bottom, we get a minus an x to the minus 2. Now we need to do a little algebra to simplify this. If we just rewrite this as 1 over x divided by minus x to the minus 2, which is the same as 1 over x times a minus x to the positive 2 over 1, then we cancel 1 power of x here. This is the limit as x approaches 0 from the right of minus x, which gives us a 0. So this limit ended up being a 0, but notice we had to do an extra step. We had to recognize this as an indeterminate form. We had to do an extra algebra step to put it in either a 0 over 0 or an infinity over infinity indeterminate form, and we then used L'Hopital's rule. Okay, another type of indeterminate form is an infinity minus infinity. If you take a look at the limit as x approaches 0 from the right of 1 over the square root of x minus 1 over x squared. As x goes to 0 from the right, this function is going to positive infinity. This function is also going to positive infinity. So this is an infinity minus infinity indeterminate form, and we don't know how this will end. We need to first algebraically simplify it to get it in either a 0 over 0 form or an infinity over infinity form, and then we can use L'Hopital's rule. So here, there's going to be some algebraic gymnastics that have to take place. So for example, I get a common denominator. I write things over that common denominator. Remember, the square root of x is x to the 1/2, so I just write this as an x to the 5/2. Now, when you have it rewritten in this form, this is a 0 over 0 form. As x goes to 0, the numerator is going to 0, the denominator is going to 0. So by algebraically simplifying, and when you have these infinity minus infinities, look to combine things so that they look like a fraction, so that you have a shot at using L'Hopital's rule. So that's what I did. I got a common denominator. This is a 0 over 0 form. I can apply L'Hopital's rule. Just do the derivative of the top, do the derivative of the bottom. I need to do a little bit more algebraic gymnastics to get this to resolve. So here, for example, the 5/2 in the denominator, I'll pull out as a 2/5. I'll rewrite this as a 2x over 1, and this is a 1 over 2 square root of x. This is then an x to the 3/2. I'll get a common denominator in the numerator and combine. I'll leave the denominator alone. This is just algebra, no calculus. And then I will rewrite this as this quantity divided by this quantity, which is the same as this quantity, times the reciprocal of this quantity. That's what I have here. Finally, we're able to combine these two terms here, and we're ready to finally take the limit. Notice, as x goes to 0 from the right, the numerator this term is going to 0, but this term is remaining a minus 1, so the numerator is going to minus 1. The denominator is going to 0, so this is going to a minus 1 over something that's getting closer and closer to 0. Notice that is not an indeterminate form. That is going to a negative infinity. So there was a lot more algebra involved here than there was calculus. There was one step of calculus, and it occurred right here when we used L'Hopital's rule. So be prepared for that as well. All right, lastly, we need to talk about what happens when you have indeterminate powers, 0 over 0 and 1 to the infinity. We want to use what I call the little logarithm stunt. So take a look at the example. As x goes to 0 from the right of x to the x, so then this would give us a 0 over 0, a 0 to the 0, 0 to the 0 form. And we need to make this where we can apply L'Hopital's rule. So the stunt that we're going to use is a little algebra property of logarithms that you may or may not remember. And we're just going to rename this as y. We're going to let y equal x to the x. If we take the natural log of both sides, this is the ln of y. This is the ln of x to the x. And you may remember the property that when you have an ln of a to the b, that's the same as b ln of a. And so this exponent comes down outside. This isn't calculus, this is algebra. This exponent comes down outside of the natural log and becomes a coefficient. And the reason that's helpful is it's getting rid of this power. And now, if ln of y is x ln of x, we can take the limit as x goes to 0 on both sides. So that would be the limit as x goes to 0 from the right of ln of y is the limit as x goes to 0 from the right of x ln of x. And if we do that, then we get, notice, as x goes to 0 from the right, we already did this in example 5. This is a 0 times a minus infinity indeterminate form. I won't redo that work here. We already did this. We saw that this limit comes out to be 0. So be careful, that's not the ultimate answer to our final problem, because this is not what y, this is not the limit of y, this is the limit of the ln of y. So just follow the logic here. If this limits to 0, that means the limit as x approaches 0 from the right of ln of y is 0. So we want the limit of y, so we'll just hit both sides with a base e exponential. This is the same as the limit as x approaches 0 from the right of e to the ln of y equals e to the 0. E to the 0 is 1. And now e to the ln of y is just y, so we know the limit as x approaches 0 from the right of y is 1, but y is just another name for x to the x. So we eventually got to our limit that we were interested in. When you have these indeterminate powers, you usually want to pull this stunt where you rename what you have as y. You take the natural log of both sides. You use this property of logs that pulls this power down, and then you go from there. See what kind of indeterminate form you have, make it to where you can use L'Hopital's rule, and then remember to convert back. It's sort of reminiscent of a U substitution. We're taking a substitution to turn a problem we don't know how to do into a problem we do know how to do. One more example of that type. So consider the limit as x approaches 0 from the right of 1 plus x to the 1 over x. Notice that this is a 1 to the infinity indeterminate form type. So again, we'll let y be our entire function, 1 plus x to the 1 over x. We'll take the natural log of both sides in order to use our logarithm property to bring this power down. Now we'll take the limit as x approaches 0 from the right of both sides. Notice that before we can apply L'Hopital's rule, we want to write this strictly as a fraction, so I'll write this as ln of 1 plus x over x. Now, if you stare at this, this is a fraction and the numerator is going to 0. This is the ln of 1 plus 0, which is the ln of 1, which is 0. The denominator is 0, so this is a 0 over 0 indeterminate form as it's presently written. We could use L'Hopital's rule then. The derivative of ln of 1 plus x is 1 over 1 plus x. The derivative of x is just 1. And so now this is a continuous function. This is not an indeterminate form. We can just let x go to 0, and we get 1 over 1 plus 0, which is 1. Now that's not our final answer. This is actually the limit as x goes to 0 from the right of the ln of y is 1. So now we'll apply a base e exponential to both sides. E to the 1 is just e. E to the ln of y is y. And then y was our original function, 1 plus x to the 1 over x. So our ultimate answer to this limit is that it's e. The last topic in this section is we want to compare growth rates of various functions as x gets really, really large and positive, as x goes to positive infinity. So to compare the growth rate of a given function f of x to that of a function g of x as x goes to infinity, we want to form the quotient f of x over g of x, and then we want to take the limit as x goes to infinity. The idea here is if f is growing faster than g, then the limit of this quotient will become very large. If the g is growing faster than f, then this limit will become very small. And if it's a tie, f and g are growing at the same rate, then the limit will be some constant that's between 0 and infinity. And the notation we use for this is we say that if f is greater than g, and if g is greater than f. This just means if f is growing faster than g, if g is growing faster than f. We don't want to use a strictly greater than because we don't necessarily know that f is greater than g. We just want to say that eventually f will dominate g. Eventually f will get bigger than g and stay bigger than g. That's another word that's commonly used in calculus. If one function dominates another, it just means that the function eventually, for a sufficiently large x, becomes greater than g and maintains that inequality. It stays bigger. So let's compare the growth rates of, say, the function e to the x and the function x squared as x goes to infinity. So we just want to form the quotient e to the x over x squared, and we want to take the limit as x goes to infinity. Now if you stare at this, this is an indeterminate form. The numerator is going to infinity, the denominator is going to infinity. So we'll just have the race. We'll let x go to infinity, and we'll use L'Hopital's rule here. By L'Hopital's rule, the derivative of e to the x is e to the x. The derivative of x squared is 2x. Notice this is still an indeterminate form. It's still an infinity over infinity indeterminate form. And it's okay to use L'Hopital's rule multiple times in a row if you have to. That will happen to you in the homework. So we'll just use L'Hopital's rule again. The derivative of e to the x is e to the x. The derivative of 2x is just 2. And now this is not an indeterminate form anymore. As x goes to infinity, the numerator is going to infinity, the denominator is going to 2. So this is the overall limit is going to infinity. So we see that the numerator is growing faster than the denominator. So the entire quotient is getting big, and we would say that e to the x dominates x squared, or e to the x grows faster than x squared. And that is a property that you've probably learned about exponential functions, that they grow faster than power functions. It turns out, and I'm not proving this, but you could perform this same race. We just raced e to the x against x squared, but you could also have a race between a power function and ln of x, and it turns out that e to the x dominates every power function, and every power function dominates ln of x. So sort of the hierarchy here is that ln of x is a very slow-growing function compared to positive power functions, every positive power function, and e to the x dominates every positive power function. So this is our hierarchy. These grow the fastest, then these, then these. And you'll see that that'll come up several times in our later sections in Chapter 7, but also in Chapter 10.